Hello, my name is Kyle Azuma. I'm an intern here at Kaksanuk as a quant analyst, and in this video, I will be presenting my project submission for the Python Foundations module. So in this project, we're developing a framework for financial data quality and validation through a Python-based system for large-scale financial data analysis. Now, before we begin, I'm just going to quickly go over the project structure, as it consists of three main components. First, the presentation slide deck, which you're currently seeing. Second, the Python code, which I'll be going over later in this video. And lastly, the written report that goes over the methodology, process, results, and interpretation in a little bit more detail. So let's begin. First, to provide some background context. Essentially, the issue that we're seeing here is that financial datasets can contain errors such as impossible prices, missing corporate actions, or even before that, broken files due to upstream pipeline failures. And so if left unchecked, these issues can have an impact as it can distort returns, invalidate models, and lead to incorrect or inaccurate economic interpretation. And so as a result, a structured validation process is required to detect anomalies and separate or distinguish true data errors from legitimate market behavior. And this brings us to our project overview, which is to develop a Python-based validation system to assess large-scale market data quality by identifying both upstream assembly failures as well as content-level anomalies, and then interpreting the results to distinguish true provider errors from legitimate market behavior. And so now moving on to the dataset and the inputs, there were essentially three main inputs that were provided to me at the beginning of this project. The first being universe information, so the general reference data for company identification and categorization. Next, the company data files themselves. So in our case, 6,081 files containing basic financial information. And lastly, the logger file, which is kind of the upstream diagnostics capturing failed downloads and assembly errors that were logged previously. Now moving on to the methodology, we've implemented a three-layer validation framework, starting off with structural integrity, so system assembly, identifying the pipeline failures and corrupted files before the checks even begin. Next, the logical constraints, so this is the content validation, applying financial rules to detect outliers, which brings us to the economic interpretation of classifying anomalies as either provider errors or legitimate events. And so now moving on to the validation logic, essentially we're going to focus a little bit more on this area here. The validation logic can be broken down into three detection categories. First, the market integrity, so price consistency, making sure that the low prices are in fact of lesser value than the high prices, and making sure that prices are greater than zero. The volume validity, so making sure that there are no negative trading volumes, as well as extreme returns. So in our case, we set a threshold of 50%, which means that if daily prices change at an extent greater than 50%, then it would be flagged as a potential issue. Next, moving on to the corporate action context. So here we're detecting explicit stock splits. And the reason for this is because stock splits can help determine whether these extreme returns can be justified as legitimate corporate events or whether they are true provider errors. And then finally, fundamental data stability. So checking to see if there are any excessive update frequencies. In our case, we set the threshold to 5% of observations. And so the reason for this is because fundamental data is usually updated on a less frequent basis, perhaps on a quarterly basis. And so if it's being changed very often, then that would be something to look out for. Next, moving on to the code architecture, we have built a Python-based automated validation engine that follows a flow kind of as follows. So first loading the inputs and the raw data, then applying the validation functions, so the set of rules, and then looping across all of the 6,081 files, aggregating the results across the data set in order to finally generate the outputs. And so at this moment, I'm going to shift over to the code. And one thing to keep in mind is that I have actually already ran the code previously, as in advance, because processing over 6,000 files does take a few minutes. And so just for the sake of efficiency and so that we're not just waiting here while the code runs, I have already gone ahead and ran it in advance. But essentially, the code consists of 9 different sections. And so I'll go through each one of them very briefly, one by one, just to provide a high-level overview as to what it is, why it's there, the purpose behind it, and so forth. So starting off by importing our libraries and just doing the basic setup. In our case, we have imported OS, pandas, and matplotlib. Next, moving on to defining the paths, so both our inputs and outputs. And so actually I can show you here. Here we have the input, which are those 3 things that we mentioned before, the universe information, the logger, as well as the data. So here we can see all 6,081 of our data files. And in terms of the output, we have created this folder just so that once the code runs and it generates its output, it can be stored inside of this folder. So next, again, loading the reference data, so the universe and the logger, so it can be accessed. Next, the actual data validation function, so the logic checks. So the set of rules that we had discussed before. So for example, here we can see that if the low price is higher than the high price for whatever reason, then it would be flagged as an anomaly. And same with all the other rules that we set. For example, here, negative trading volume detected. Here, the extreme returns. So if the daily return exceeds our threshold. Here are the unstable fundamentals. So if the fundamental values are changing too frequently, more than our threshold. And lastly, every time a stock split is present, then it would be detected and flagged. Now, moving on to the main file processing pipeline. So this is where all the loops take place, essentially where it loops over all 6,081 of our files. And then once that's done here, we're aggregating the output, our flagged issues. So essentially what it's doing is aggregating all the detected issues, packaging it into a CSV file, and storing it inside of that output folder that we just saw. Same thing with the logger summary. So these are more so for the system level failures. Again, it's going to aggregate all the failures, package them into a CSV file, and store them in our output folder. Next is the visual summary. So just creating a very, very basic bar chart using matplotlib that kind of shows the extent to which how many issues were detected, which categories they fall under, etc. And then finally, the console summary, which is basically just everything you see here. Once again, I did run the code in advance, so we can see here that it processed all the files, the analysis was completed, and it shows just a little summary. So now just to quickly show you what gets produced as the output. First, we have the flagged issues. So here, it shows all the anomalies that were detected. Similarly, for the logger summary, all the system level failures. And then lastly here we have the bar chart, the simple bar chart. So moving back to our slide deck. So as a quick snapshot of our results after running the code, we can see that out of the 6,081 files analyzed, there were 186 system level assembly failures and 5,993 content level validation issues. So again here, just going into a little bit more detail, we can see the 186 logger assembly errors on a system level, and then from a content level, there are 66 cases of price inconsistency, 3,414 instances of extreme returns, out of which 2,500 of split events detected. Here, 13 cases of unstable fundamentals, and actually 0 instances of negative volume. So now diving a little bit deeper into the interpretation. first, in terms of market data integrity, we can see that there were 66 cases of price inconsistencies. And so these are kind of the hard errors, right? The violations of basic market mechanics. And so the affected observations would need to be corrected or excluded. Next, moving on to corporate actions, we saw that there were 3,414 cases of extreme returns detected, as well as 2,500 split events. And so the interpretation here is that in most cases, split events can justify and explain the extreme returns as legitimate corporate events, but then it still gives us 914 remaining unexplained cases that are likely adjustment errors. So this would need to be further revised and reviewed. Next, moving on to the fundamental data stability. So there were 13 cases of high frequency updates, which again is inconsistent with the more quarterly reporting norms. And so here, for example, we can set a set of rules or restrictions so that it can't be updated so frequently to reduce the noise, or be adjusted accordingly. And then finally, there were 0 cases of negative volume detected, and so that is kind of a validation success signal and indicates strong baseline from the data source. So now moving on to the conclusion, these are some of the key takeaways when we take a step back and look at it from a bigger picture. So we can conclude that approximately 3% of the total files failed system assembly validation due to upstream issues. Approximately 20% of all validation checks flagged content level issues. And then amongst those 20%, many of the anomalies are actually economically explainable, reflecting legitimate corporate actions, usually reflected by the stock splits, which means that provider errors were relatively infrequent, systematic, and identifiable. And so therefore, we see that separating system failures from content anomalies is key for robust interpretation. And so as a final concluding remark, we can take away that structured financial validation is the foundation of reliable financial modeling and trading decisions. Thank you.